through projects. In this video, we are going to explain about the project, which is longitudinal tear detection of conveyor belt based on improved YOLOv7. Before getting into the execution, first let us understand what is the project about. So you know, right, that belt conveyors are really essential in industries like mining and manufacturing because they help move materials around efficiently. But there is a catch. They can be prone to various issues, especially in harsh environments. For instance, you might find that these conveyors experience problems like tears, surface damage, and misalignment. So these issues they often stem from things like improper installation, impacts from sharp objects, or even uneven loads. So if we don't catch these problems early on, it can lead to some serious consequences. We could see equipment failures, safety risks of workers, and a lot of downtime, which in turn leads to significant economic losses. So, it is crucial to have a reliable monitoring system to detect these issues before they turn into a bigger problem. It really emphasizes the need for ongoing vigilance in maintaining conveyor belt systems. So, when it comes to detecting these issues with conveyor belts, there are some traditional methods we have relied on, like contacting lens, and we have contacting sensors, ultrasound, electromagnetic induction, and even X rays. However, each of these has its drawbacks. For example, they can be quite expensive, prone to false alarms, or even pose safety risks, which isn't ideal in industrial setting. So now machine vision has been promising alternative, but it often struggles with the poor image quality in those tough environments. So this can lead to missed detections or false alarms, which can be really frustrating. Even though we have seen advancements in the deep learning and the models like YOLOv3 achieving reliable real-time detection, it is still a significant challenge. This situation really emphasizes the urgent need for better monitoring solutions that can ensure the safety of conveyor belts while minimizing any disruptions to operations. It is clear we need to find something that works more effectively in these demanding conditions. So, to overcome the above problems, in this project, we are integrating deep learning approach. I mean, we are incorporating some deep learning approaches for detecting the longitudinal tears in the conveyor belts. So, we are using the data set which is captured from the linear CCD camera. So, here we are detecting longitudinal tears in the images of the conveyor belts which are captured through this linear CCD camera. And once we have those images, we process them with a modified version of the YOLOv7. And here, this isn't just a version, we also have integrated efficient intersection over union loss function, which really helps to boost the model's performance. And to improve the detection accuracy even further, we have added a simple parameter free attention model that is SIM-AM to detection ahead. This module helps the model focus better on the important features in the images. Additionally, we are using new component that is SIM SPPFCSPC module. This helps speed up the detection process without sacrificing precision, which is crucial when you are operating in a challenging industrial environment. So this is all about the proposed system. Moving on, as an extension to further improve the performance, we have incorporated the latest advancements in the deep learning by using the upgraded versions of the YOLO, which are YOLO V5X6, YOLO V8, and YOLO V9. So these models they offer improved capabilities for analyzing and detecting tears in the conveyor belts, helping us to enhance the accuracy and also the efficiency of our detection process. On top of that, we have also integrated front end. That means we have developed front end using Flask framework. So this is a significant addition because it allows us to create a more interactive platform for our testing. With this interface, users can easily engage with the system, and we have built in authentication features to ensure that the experience is secure. Overall, this extension not only boosts the analytical power of the project, but also makes it more user friendly and accessible for those who will be using the real world application. Moving on, so we have followed the steps in the flow of work to implement the project. So first, we started by importing the essential packages for image processing, machine learning, and data manipulation, and also the web development. Then we have explored the data set where we load images from the data set to familiarize ourselves with the data, and then we visualize the images to assess their quality and the features. And then we prepare images for model input by converting them into the blob objects. And then we establish the classes that model needs to recognize, and we set the bounding box around areas of interest in the images. And we change the data into NumPy arrays for easier processing. And then we load the pre-trained model. So we load pre-trained model and read its network layers, and we extract output layers essentials which are essential for making the predictions. And moving on, here we create annotation files linking images to their labels, and we change image format from BGR to RGB, that is blue, green, red to red, green, blue, for accurate color representation. And we generate a mask highlighting areas of interest. And we resize images into a consistent dimension for model input. And then we apply some random transformations to increase data variability. We rotate images to enhance the diversity, and we perform transformations like flipping and cropping. And then we adapt data processing techniques to align with the YOLO model requirements. And we construct models, and then we will be constructing models defining layers of the YOLO framework. And then we train the model on annotated images, allowing it to learn defect recognition. And we will be saving the best performing model for future defect detection without retraining. And we develop front end using Flask framework with the user registration and login supported by SQLite 3 database. And users, they will be uploading images for the defect detection via the front end, and that input will be pre-processed at the back end to prepare it for detection. And then we feed it with the trained model, that is, we feed the pre-processed image into the trained model for defect detection, that is the longitudinal tear in the conveyor belt. And the display detection results on the front end, providing immediate feedback to the users. That means whether there is a longitudinal tear on that particular image or not. Moving on to the algorithms used, these are the algorithms used in the project, and the last three are the extension models. So the algorithm which performs best among all these models, we will be using them in the front end. So the extension models have performed well, so we will be using them in the front end to detect the longitudinal tear in the conveyor belt. Moving on to the implementation. So we need basic requirements which are hardware and software. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap. Now let's execute. To execute, we need to open the code folder which contains source code files. So let's open the code folder of the project. These are the source code files in the code folder of the project. So here in the first four folders, we have the data set used in the project to train. Let's discuss about this after discussing all the folders. And here in the sample folder, we have the test cases that we will be using in the front end to detect the longitudinal tear in the conveyor belts. Coming to the static folder, this folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal of the project. Coming to the templates folder, this folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And coming to this app.py file, this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And this is the model file which contain the algorithm information. So this will be loaded into the project code during runtime of the application. And this is the notebook.ipynb file. This is a Jupyter notebook file which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And coming to the signup.db file, this file is a database file which is used to store the user information. And now let's see with the data set. So let's open the first conveyor belt YOLOv7 PyTorch folder. Let's open it. So here we have two subfolders. One is train and valid. Let's open the train folder. And in train, we have two more subfolders. One is images and the other one is labels. Let's open the images. So these are the conveyor belt images that we have used in the project to detect the longitudinal tear. So we will be using all of these images to train the models in such a way that they will be able to detect the longitudinal tear. So we have total of 631 images in this images folder. Get back. Coming to this labels folder, here we will have the files containing annotations or the labels for the objects in the corresponding images. So here each label file corresponds to an image file in the image folder. So this label file, it corresponds to this image, and for this particular image we have this corresponding label file which provides the objects, locations, and classes within the image. Similarly, for all the 631 images, we have 631 label files. So these label files, they often follow the YOLO format where each line represents a detected object. Let's open an file, for example. So here, this line represents a detected object and each line specifies the object's class index. So this specifies the object's class index and these are the bounding box coordinates. So this is the x limit, this is the y limit, this is the width, and this is the height. So let's close this, get back. So the images and the label files which we have in the train folder, that will be used to train the models, and the images and the label files which we have in the validation folder, we will be using them in the validation purpose. That means we will be using them for the testing purpose, that how well the models have been trained, and that will be predicting on the unseen data. So similarly, we will have here images and labels. Get back. Similarly, we will be having in the YOLO V5, YOLO V6, YOLO V7. So each folder contains the same images, but they are annotated differently because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. Having separate folders helps to keep the dataset organized, ensures that each YOLO version receives the correct annotations it needs to function properly. So now we have to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now let's open the Anaconda prompt. So here, Anaconda prompt is open. Now using the command cd followed by the space, paste the copied path and now click on enter. Here, current directory is changed to the code folders path. Now we need to compile app.py file. So give the command python space app.py and click on enter. This will change. I mean, after running this app.py file, the application will host the web application at the local address, that is the local host and the port, unless configured differently. And this command, it will execute the Python script and perform a runtime check for any syntax errors or logical issues. So layers are being fusing. I mean, it is fusing the layers. So this is the link. So this is the local host and this is the port. Now we need to copy this local link provided by the Flask framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome. So let's open that. Paste the link here. Click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. Let's register first. Click on register. And here we need to fill in all these registration details to register. I have already registered, so I'll directly sign in. Click on sign in. Give your username and the password. Click on login. We have logged in successfully and we are redirected to the detection page of the project. So here you can see a choose file button, right? We need to click on that for uploading the images. So click on choose file. These are the test cases in the sample folder. Let's upload them. So let's upload the first image. Click on open. It's loaded. Now upload it. Image will be pre-processed at the backend and the train model will give us a detection. So here we have a T detection in the conveyor belt. So this is the conveyor belt and here we have the detection in the blue color bounding box where it has 0.77 probability score. Probability score, it means that model's probability in predicting how accurate the tear is. That is, it is 77% correct that it is detecting tear. Let's try using some more images. Click on choose file. Let us upload this image. And here we have the detection. So it is detected in the blue color bounding box. And this is the conveyor belt. Let us upload some more. Let's try uploading this one. And here we have tear detected. So this is the conveyor belt. And here we have tear detected with a 0.79 probability score. That means the model is correct of 79% in detecting this tear. Now get back. Let us try using this image. Click on upload. And here we have the detection. So this is the tear detected in the conveyor belt. So this is the conveyor belt and this is the tear detected in that particular conveyor belt. Let's upload the last image. Click on choose file. So let us upload this image. Click on open and now upload it. So this is the conveyor belt and here we have the tear. Now get back. Let's check with the graph. So click on graph. So here we have the precision and recall graph of YOLO model in predicting the tear. So here we have blue color, light blue represents the tear with the 0.65 precision recall score. And here we have all classes, that is 0.65 mean average precision. And here we have FN score graph. And this is the confusion matrix. And here we have precision comparison graph, where on x-axis we have precision score and on y-axis we have the algorithms used. And this is the recall comparison graph. This is the mean average precision comparison graph. Mean average precision, recall and precision, these are the metrics used to evaluate the detection models. Now click on logout. In this widget, by uploading images to the system, the YOLO model, it will accurately detect the tear identified in the conveyor belt. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.